and the next chapter is first law of thermodynamics. In the previous lecture, we have discussed the zeroth law of thermodynamics. Now, today we will discuss about first law of thermodynamics. Actually, first law of thermodynamics is nothing but the conservation of energy, and first law of thermodynamics is formulated on the basis of few observations. And what are those observations? The first observation is the equivalence between heat and mechanical work. Equivalence between heat and mechanical work. That means heat can be converted into mechanical work and mechanical work can generate heat. This is the first observation. So, whenever some amount of work is done, an amount of heat is produced or dissipated. This is the keynote of first law of thermodynamics. Second observation is a body in a given macro state, has definite internal energy. And when the body passes from one macro state to another macro state, suppose it is going from system A to system B. We have already stated that thermodynamics always deals with macro state. So, the system is going from A to B, one macro state to another macro state. Its internal energy changes, but the observation is it is independent of path. When the system is going from state A to state B, its internal energy U changes, but it is independent of path. That means the system going through this path, through this path, through this path from initial state to final state, that means A state to B state. Internal energy is independent of path. That means if we go through this path, through this path, through this path, internal energy change is same. Third observation is adiabatic work done. In adiabatic work done, there is no heat exchange between system and surroundings. As you know, in adiabatic process, there will be no interaction between system and surroundings. And it has been found from experiment, when a system passes from one initial state to final initial state, work done is same for all adiabatic paths. Just in adiabatic process, there is no heat exchange between system and surroundings, and the work done produced during adiabatic process, suppose system A is going to system B, it is an adiabatic process, no heat is taken or rejected to surroundings. So, and the work is done in case of adiabatic process, whatever positive work done, negative work done, or work done by the system, on the system, whatever, and it has been found that work done is same for all adiabatic paths. That means there must exist a function whose value at final state minus initial state equals to adiabatic work done, which is called internal energy. It is independent of path, means there must be a state function phi. If we integrate d phi, suppose du internal energy, we are integrating 1 to 2, that means I state to f state, u f minus ui is the change of internal energy, I to f through this path, u f minus ui. That means the final value of the internal energy, initial value of the energy, if we differentiate, we get the change in internal energy. It is a state function, so that is why we can get this form u f minus. If it is path dependent, then this equation we cannot write this equation. So, in adiabatic process, I am repeating, there must exist a function whose value at final state minus initial state equals to adiabatic work, which is called internal energy. Suppose questions come, what is internal energy, defined internal energy, you have to say in adiabatic process there exists a function whose value at final state minus initial state equals to adiabatic work done, which is called internal energy. Clear? Now, we are coming to non-adiabatic work. In case of non-adiabatic work, the difference of internal energy is not equal to the work done. In adiabatic work, the difference of internal energy is equal to the work done, but in case of non-adiabatic work, it is not true. So, some energy has been transformed between system and surroundings. So, there must be a heat exchange, something exchange, we are coming to heat later, something exchange between system and surroundings. And this energy transformed between system and surroundings is due to the thermal interaction, which is determined the difference of temperature. The interaction between system and surroundings will happen if there is a difference of temperature between system and surroundings. This is what we call heat. So, first law of thermodynamics on all of this observation, it takes the mathematical form dq is equal to du minus dw. In case of adiabatic work, no heat exchange between system surroundings. So, dq becomes 0 in case of adiabatic work, and you see the observation dw is equal to du. That means internal energy changes is equal to the work done, but in case of non-adiabatic work dq not equal to 0. So, there must be a heat exchange between system and surrounding, and we get the equation dq is equal to du, internal energy change minus work done. In some books you will find dq is equal to du plus dw, where dw is dw defined as pdv, but in I have used dw is equal to minus pdv. So, we are taking the form dq is equal to du minus dw, ultimately it takes the form dq plus pdv. This is an important equation which is the first law of thermodynamics. So, the mathematical form of first law of thermodynamics dq is equal to du plus pdv. It is very important equation, it only signifies the conservation of energy. And suppose what is adiabatic work done? Give an example of the adiabatic work done. This portion I think did not came in the video. So, I am repeating dw is equal to, in some books dq is equal to du plus dw, as they define dw is equal to integration of pdv, but in my case I have defined dw is equal to minus pdv. So, that is why we are taking dq is equal to du minus dw, that means du plus pdv. So, suppose someone says what is the give an example of the adiabatic work. Suppose a T, there is a T in the thermos, that is means it is in a thermos, that means it is in a container which is thermostat. This is called thermos. When the T in the thermos is shaken, work is done on the T against the viscous force present in different layers of the T. This causes an increase in internal energy of the T. This is an adiabatic process. I am repeating, we have a T in the container which is container which cannot transfer heat from system and surroundings. This is called thermos. So, is in a thermos and it is second. What will happen? Temperature will rise because there will be a viscous force between the different layers of the tea, and temperature will increase due to the work done on the system. That means we do the work done on the system and its internal energy will change, but it is adiabatic process because there is no heat exchange between system and surrounding. Suppose when a tire burst, its air expands suddenly into the atmosphere, it is an adiabatic process because the air expands suddenly that it cannot take heat from outside. Hence, the air does work against the external atmosphere and its internal energy changes. So, if a tire burst, what will happen? It is sudden expansion of gas and it is sudden process. So, there will be no heat exchange between system and surroundings, and the gas will expand by taking heat from the system. So, its internal energy will decrease. It is also an adiabatic process. So, first law of thermodynamics, dq equal to du plus dw. It is very